Hello, my name is Eduardo Martins, and this is my video lab report for Lab 2 for Physics 2211. The objective of this lab is to observe and analyze the motion of a falling object, and later compare it with computational models, and see how the drag force created by its interaction with the air around it makes it slow down to a terminal velocity. By the end of this lab report, we're going to see that lighter objects are much more susceptible to the effects of drag, and therefore arrive at this terminal velocity much faster. We'll be using a physical model that considers the drag force to be always opposite to the velocity and proportional to its magnitude squared. We'll also use Newton's second law that states that the change in velocity over time or its acceleration is directly proportional to the force applied to it, F equals ma. I used a plastic bag for the observation due to its light weight and compared it to the falling motion of an eraser that I had lying around so I could prove the presence of the drag force. At the beginning of the video, both of them are at rest, but as soon as they start moving, we can see that their rates of change of velocity and position are different due to the presence of the drag force that acts much more significantly on the lighter body. Now let's watch the video. As you can see, the eraser falls much quicker than the plastic bag, and that's due to the effects of the drag force. Here we can see the position and velocity graphs over time of my tracker data and both of the physical models I simulated using GlowScript. The blue one is the one that does not take into account the drag force, and therefore we can see that the velocity and the position are much greater in magnitude than the other ones. The difference is so big that we can't actually see how the other graphs look like. So here we're disconsidering that one and just looking at the situations where we're considering drag. We can see a clear difference between the observations and the simulations, but the overall shape of the graphs are very similar, and that's probably because we're using an accurate model, but there are lots of little mistakes in doing the measurements in the tracker phase or when I try to calculate the drag coefficient, which I'll show in a few moments. But in both cases, we see that the object's velocity approaches a constant value after less than a second, and that's the terminal velocity, which happens when the drag force caused by the velocity is equal in magnitude to the gravitational force, and therefore the net force is zero, which means the velocity doesn't change. And so in the velocity graph, we see a constant value, and in the position graphs, we see a constant slope. Now, to approximate the value of the drag coefficient, I wrote a Python script that would look through all my tracker info and calculate the average drag force over each time step and then give me the average. So that might be one of the sources of error, since the iterational approach only arrives at approximate values. Now, for the actual simulation code, I first approximated the object's mass and then used the tracker info to determine everything I needed to set the initial conditions and properties of my system, which in real life was just a plastic bag, which was affected by gravity and drag, and in the simulation is just a ball. After that, I just made a simple loop that would calculate the drag force based on the current velocity, use it to determine the net force, and then update the velocity, and with that new velocity update the ball's position. With this same simulation, I also tested what would happen if the initial velocity wasn't zero. I used -3 meters per second, but it could have been any value. We can see that no matter what I choose to be the initial velocity, the terminal velocity will always be the same, and that actually makes sense because the terminal velocity is just the one that makes the drag force nullify gravity. And since the drag force is proportional to the square of the velocity, it will always be the same, no matter what the initial state is. In conclusion, we can see that in contrast with what we usually see in physics problems, in reality we actually do need to account for the drag force caused by the interaction with the object and the air around it. And the lighter the object, the stronger this relationship is, and the more its motion is influenced by the air around it. Thank you.